basic definition of stereochemistry is that it is a subject which deals with the property of a molecule in three-dimensional space. It is becoming increasingly important in the study of organic chemistry because it has significantly contributed in establishing the mechanism of organic reactions. Important biomolecules like steroids, carbohydrates, proteins, and nucleic acid have a fascinating stereochemistry of their own. I would like to explain the concepts of stereochemistry from the very beginning. So let's talk about some history here. It all started with the discovery of plane polarized light, thanks to Christian Huygens, who was a physicist from 17th century. Now we know that light is an electromagnetic wave. So it has two vectors. It is an electrical vector like this and a magnetic vector like this. And these two vectors are perpendicular to each other. And these two vectors are also perpendicular to the direction of propagation of light. Now, if we consider only the electrical vector, then in a normal light, the electrical wave vibrations are taking place in all directions, and this is a normal unpolarized light. We can see here the electrical vibrations are taking place in all directions. But Huygens discovered something called plane polarized light. He made the normal unpolarized light to fall on a calcite crystal, and then he got polarized light in which the light propagates in a single plane. It is called as the plane of polarization, and the vibrations from this light will also be in a single plane, which will be perpendicular to the plane of polarization. Now, in this calcite crystal, the principal axis is in this direction. So, the vibrations will take place in this plane. Now, if we have another calcite crystal here, and the principal axis is in this direction, then it will completely block the propagation of light, and we will see complete darkness here. Now, if we rotate this crystal to 90 degrees, the principal axis of this crystal will be coaxial to this crystal, so the light will propagate without any disturbance, and we will see complete brightness here. Then a scientist called Biot in 1835 found out that there are some molecules which rotate the plane of polarized light to some extent. Now he placed an optically active sugar solution in between these two crystals and found out that there is a change in the angle possessing the plane of polarization. Initially, when this optically active sugar solution is not kept in between these two crystals, no light was coming out from this crystal. Since this principal axis and this principal axis are perpendicular to each other, no light was coming out. But as soon as he kept this optically active compound in between these two crystals, there was light coming out of this crystal. And then when he rotated this crystal to some extent, say for example 30 degrees, then again no light was coming out. So this means that this molecule, this optically active sugar solution, has rotated the plane of polarization of light by 30 degrees. This phenomenon does not happen with all compounds. If we place an optically inactive compound here, the plane of polarization will not be disturbed. Now the reason for this rotation of plane polarized light was not known by that time. Then in 1847, Louis Pasteur involved himself in analyzing the tartaric acid, which was extracted from grape juice fermentation. What he did was he collected this tartaric acid and crystallized it as sodium ammonium salt. As it is a dicarboxylic acid, one H will be replaced by sodium and other H will be replaced by ammonium ion. Now after crystallization, he noticed two kind of crystals. One is this and the other is this. He could separate these two crystals using a microscope. When he tested the optical property of these two crystals, he found out that one crystal rotates the plane of polarized light in the positive direction, that is the clockwise direction, to some extent, and the other rotates the plane of polarized light in the negative direction, that is the anti-clockwise direction, to the same extent. Now, if we didn't separate this crystal, it would have been in a racemic mixture, which is the 50-50 mixture of these two compounds. This racemic mixture does not rotate the plane polarized light because one half of the compound will rotate the plane polarized light in the clockwise direction and the other half cancels it by rotating it in anti-clockwise direction. So the angle of plane polarized light will be undisturbed or unchanged. These are the two crystals which was obtained by Louis Pasteur, As we can see here, one compound is the mirror image of the other. If you keep a mirror in between these two compounds, one will be the mirror image of other, and these two mirror images are non-superimposable. As we try to superimpose these two compounds, we can see that the H and the OH mismatch in every position. So these two compounds are non-superimposable molecules and exist as enantiomers. Now this here is a two-dimensional representation of that three-dimensional molecule. This is basically Fischer projection. We will learn about Fischer projection a little later. So in two-dimensional chemistry, tartaric acid looked as a single molecule, but since they have different rotatory power, this cannot be the same molecule. So the molecule which looks the same in two-dimensional view really exists as a two compound in three-dimensional view. Pasteur also studied another form of tartaric acid, which is the mesotartaric acid, which he could not separate into two compounds, that is two isomers. He thought that this compound would be optically active. Since this is a single compound, he thought that this must be optically active, but to his surprise, it was optically inactive. This optical inactivity is due to the internal compensation of plane polarized light by this mesotartaric acid, whereas in racemic mixture, one effect is equally nullified by the other. So external compensation occurs in racemic mixture. In here, due to this plane of symmetry, internal compensation occurs. So Pasteur actually found three types of tartaric acid. The first one is called plus tartaric acid or the dextrotartaric acid. The second one is minus tartaric acid or the levotartaric acid. And the third one is mesotartaric acid. In this 3D structure of mesotartaric acid, you can see here there's a plane of symmetry here. Now the upper part of this molecule is the mirror image of the lower part of the molecule, and that's why internal compensation occurs, and that's why it is optically inactive. Now Pasteur could not able to distinguish between this meso compound and its mirror image, which is this. Now if we place a mirror here, one compound is the mirror image of the other, and he could not separate these two compounds because these two are the same compounds. Now if we rotate this compound to 180 degree like this, I just rotated this compound to 180 degree, keeping this as an axis, and if I try to superimpose it now, we see that every atom gets superimposed perfectly. The OH and the OH match, the H and the H match, and this H and the H match, and this OH and the OH match, and COH and the COH also match. So the mirror image of a meso compound is the same compound, and that's why Pasteur couldn't able to separate the mirror image of meso compound.